You guys have heard of things like clustering? What do you think is clustering? Clustering, basically, I have a bunch of points and I'm trying to see, maybe there are, this corresponds to class C1 and this corresponds to class C2. So I can just basically make up this class which I never even noticed and say it will be 1 for one set of points and 2 for the other set of points. And then just try to figure out which is which. And EM will tell me. And when EM tells me, I got clustering. Just this one idea basically also gets you clustering. And in fact, what I have here actually is if I have both, what do I call this? Semi-supervised learning. Lots of jargon, all just falls into place. Semi-supervised, semi-supervised. Can you do semi-supervised learning? Now you can. Is it any harder? No, you just put your naive-Bayes classifier in a loop and just keep going round and round the loop. All you just do is compute the data likelihood across the iterations and stop when the likelihood doesn't increase anymore. Now, why is this useful? Turns out in many scenarios, labels are hard to get. Web basically made machine learning much more effective because web has humongous amount of data of certain kinds, like natural language data, image data, even audio data, etc. Everybody can access it. The tricky part is it doesn't necessarily have labels for the data. So for example, suppose I was thinking of a situation where this is instead of Russell's restaurant example, if this is spam mail. I have a huge amount of mail to my inbox. Google basically has access to all of it. Larry Page is every day reading it. It says he doesn't, but he's reading it. Right? Some of them I read and I put in the trash. Then he knows, oh, Rao thinks this is spam. Right? So some of the mails he knows the labels. But there is a whole bunch of other mails which he still doesn't know whether I consider it trash or not trash because maybe I haven't yet looked at them. So that's basically would be like, these are all the mails for which I know whether they're spam or not spam. These are all the mails that Rao did get, but I don't know the label. Can I use them? Of course you can. And am I just making this whole thing up? Or do we essentially have proof for this? In fact, here is a pretty old set of data where essentially they are, first of all, you understand that a learning algorithm improves its accuracy as more and more training data is given. So here the number of labeled documents, the number of labeled mails that are labeled spam or non-spam is increasing this way. Now, I have two algorithms. Algorithm 1, which just uses the labeled data, naive-Bayes classifier. Algorithm 2, which uses naive-Bayes classifier with the unlabeled data. It's been given extra 10,000 unlabeled mails. This first guy said, I don't have, I'm not the kind of guy who will do problems which have no solutions. This guy said, give it to me. And he's using EM. And these curves show the accuracy on the test data. And notice what is happening. Basically, you're not surprised, you shouldn't be surprised that both of them come to the same point after a large amount of data. What's much more interesting is here. With the same amount of labeled data, having access to unlabeled data should help you. Now here is an interesting question to ask yourself. And of course this whole thing looks like you're getting something out of nothing. This looks like perpetual motion machine of the AI kind, right? Yes. How do we stop this worry that it's not perpetual motion machine? So here is one idea. Suppose, so for example, if these are, so basically let's say, instead of spam mails, let's say these are Russell's restaurant waiting habits problem, and these are the Russell's restaurant waiting data. And these 10,000 samples, I just made them up. I know that I don't have to give you answers, so just made them up. I just made gobbledygook problems in the math textbook. In fact, if I was a math textbook writer, and I know that I don't have to give answers to all the even numbered problems, why bother making them actually solvable? Because I know none of you are going to solve it. So I'll just write some number of words and some sentences and a couple of mathematical symbols and stop. And it looks like a problem, but it's not a problem. Would that improve your learning? No. For the people who don't actually use problems without answers, it doesn't affect their learning because they never looked at them before, they won't look at them now. For the people who actually try to solve the problems without answers, they are hitting their head and throwing the textbook out the window. Do you understand what I just said? Yeah. Now, so what do I need to do to make sure that the 10,000 unlabeled documents? So first of all, what that says is, I can give you unlabeled documents that may not improve your performance at all. Or unlabeled examples that may not improve your performance. So in particular, for example, I might have given you restaurant waiting habits of raw, because raw is easily available. And you get 10,000 examples of raw's restaurant waiting habits, which are unlabeled, and Russell's for which they are labeled. Do you think 10,000 unlabeled examples for raw would help Russell restaurant scenario? When you say that, when you say no, obviously you are stereotyping of some kind. You're somehow thinking that I'm very different in my restaurant waiting habits than Russell is. More importantly, what you're really saying is, if the unlabeled documents were drawn from the universe of samples with the same distribution as the labeled samples, the only difference is after they draw them, you just remove the label. If that were to be the case, then they would work. If not, they won't. Again, that idea of distribution becomes very important. Do you see what I'm saying? So, for example, I can give you spam mails and non-spam mails from my mailbox, and I also give you a whole bunch of New York Times articles and say, oh, these are unlabeled, just use them. You shouldn't expect them to be useful at all. Because they are not drawn with the same distribution as the mails I get. My mails seem to be, can you extend the deadline, mostly. Okay, whereas New York Times has all sorts of different kinds of articles. So the distribution seems to be very different. And so adding unlabeled samples from a different distribution is not going to help me. Which is the way you know that it's not perpetual motion machine. Because you're not just generating samples out of nowhere. Somebody actually took time to write this mail and sent it to me. And this mail is representative of the kinds of mails I get. I just haven't made a decision as to whether it is spam or non-spam. So everything else is the same. So in particular, I can't just make a bag of words and say, hey, this is a mail for Rav. Unless Rav is just getting bag of words every day. Do you understand what I'm saying? So it's a very deep point again, because unlabeled examples work, in fact, if they are from the same distribution as the other training data, as well as, of course, the test data. Okay? So, going back to this, basically how the naive Bayes will work in this case is essentially, it will, you could, instead of just starting by just arbitrarily initializing the parameters, you could initialize the parameters of the naive Bayes using just the labeled examples. And then take the naive Bayes classifier you get to predict the class distribution for the unlabeled examples. Now you get a bunch of fractional samples. Now you have more samples. Use them to recompute the parameters of the network. Use them to rechange the probability distribution for the unlabeled examples. And keep doing this. Okay? This is basically semi-supervised learning. Here is another example which is actually described in textbook. See, textbook basically just talks about this candy because he's crazy about candies. Okay, but spam is just as good, and semi-supervised learning, understanding that EM is the basis for unsupervised and semi-supervised learning is very, very useful. Extremely useful. Okay, so in this particular case, if the bag is not, so basically I'm getting a bunch of candies and they're being drawn from 2 or 3 different bags, and the probability of the flavor and the wrapper and the whole depends on which bag I'm drawing the candy from. Except I did not see the bag. In fact, this is almost the same as one of the examples we discussed earlier, except in that time we looked at all the variables. Here I'm not looking, I never get to observe the bag. So this was a case where essentially this is basically clustering the examples into you are of type bag 1, you are of type bag 2. Completely unsupervised learning. Right? Yes?
Maybe you captured this in your explanations, but what if after we learn the parameters, we are generating data and we consider it unlabeled and we use it again to retrain our classifier? Does it make any sense?
Meaning what? So you're saying you're going to take even the labeled data and relabel it?
No, I'm taking the network that I've designed the parameters for, and I'm regenerating data and say this is unlabeled data.
That does not, okay, so that's a very good point. So that basically, so what he's saying is if I ever generate, so in this case, it's a good question by the way, it's a very nice question. So what you're saying is, instead of me giving you these unlabeled examples up front, suppose I only gave you these. Suppose I only gave you these. And you learned a naive-Bayes classifier with this. And his insight is naive-Bayes classifier is generative model. So it can generate data. Okay, could I then use it? Now, honestly, naive-Bayes classifier generates data with labels. Why would you want to do any better by removing the labels that it's generating? So if you think intuitively, first of all, even if you just generate the data and from the naive-Bayes classifier, that cannot change the distribution because the distribution is generating the data is generating the distribution. Data is being used to get the distribution. And you're doing one worse. You're actually generating the data and removing the label. And you're expecting somehow that should improve the distribution. That's not going to happen. But it's a good question to have. These are reasonable questions to have as to where is this unlabeled data coming from. Well, once it looks like I can have perpetual motion machines, you should have more ideas of perpetual motion machines. This was another one. This one is actually a perpetual motion machine. And so it's not going to improve. Here I am giving you information that you don't have, in essence. I'm giving you more points on the true distribution. Okay? So anyway, so basically I will get, I will initialize the network with the samples, with the complete samples, network parameters with the complete training data, and then recompute the posteriors for the unlabeled training data and relearn the network. And we already said that actually, I was in the middle of this other one. So in this particular case, there is an example in the textbook. I'm not going to go through it step by step. You should read it. Again, essentially what they'll do is they will start by, let's say, initializing the parameters for all the probabilities this way. Why this? They just started that. Okay? Then using that, they can, in fact, knowing these values, then for each of that parameter, for each of the examples for which you don't know the bag, you can compute the bag value, the probability of the bag, the distribution of the bag value. And now you have more examples with actual information about the bag variable. Then you use that to recompute the parameters. And as you are doing that, here is a picture that is showing how the maximum likelihood of the data that you provide is changing for newer and newer networks. Because you had originally one network with these parameters, then there is a new set of parameters, then there is a new set of parameters. Are these newer sets of parameters changing anything? In particular, they're changing the likelihood of generating the data you actually observe. And you'll see that the likelihood is actually increasing. And you also see that after a while, it sort of plateaus. And at some point of time, you can just stop and say, I've done enough iterations and this likelihood is not changing as much, so I just stop. Okay? And so, that gets with exactly 5 or 10 minutes left, it gets to the mathematics of why does expectation maximization work. I'm not going to run you through the full theory, but I want to give you an idea as to where the intuition, why the theory makes sense. So, remember you're computing the likelihood. Now that you're essentially, so u and theta, let's say theta are the prediction variables and u are the input variables. And you're trying to, and so you saw some bunch of examples for which you have seen some of the prediction variables, some of the input variables, and you're trying to compute their likelihood using the network. But then some of the variables are not actually observed. Those are the J variables. Those could be from the theta or from the u, from the input or the prediction variables. In fact, Bayes networks don't care. Everything is prediction variable for them. Okay, but J is the set of variables that are not actually observed. Now, if you're computing the data likelihood for each data point, you need to know the complete data. If you actually just happen to say, I only saw a marginal data, that means some variables are not observed, then really the probability of seeing the marginal data is the sum of the probabilities of seeing the completed data. So, in particular, suppose I have a network like this. A gives, A causing B. Right? So, if I have a network A causing B, then if I just have, I basically looked at a bunch of examples where B equal to 1 and I don't know what A is. What is the probability, likelihood of this example given the network? I know. That could be because this could have been caused with A equal to 1, B equal to 1, or A equal to 0, B equal to 1. And I have to sum those two probabilities. Marginalization involves summing over the missing variables. In the continuous case, marginalization involves integrating over the missing variables. Right? So, the likelihood actually, this is a log of the likelihood of the data that is seen. In the complete case, this would be a big product of each of the data points. And so it will become log of sums. And so log of products, it will be just sum of logs. But here, it would be log of the sum over the missing variable. This is what I mentioned, that logs don't like sums inside them. In this particular case, essentially, this is a kind of a function which is not easy to simplify. It doesn't just become sum of logs. It's just log of some complex sum. Now it turns out that there is this idea called Jensen's inequality, which basically says that so what it basically says is this is log of sums, and the sum of logs, it's basically winds up connecting sum of logs to log of sums as a bound, as a lower bound. Jensen's inequality is a general inequality that we wind up just using in this particular case. What I want you to understand basically is that since this is a lower bound function, the likelihood function that actually that this might correspond to might look something like this. What's bad about this is that it's not unimodal. It might have more than one maximum. However, it turns out that by Jensen's inequality, I can construct a function which is guaranteed to be lower bound for this function at this point. And if this function is guaranteed to be always below this function, then, and I'm trying to climb to the maximum of this function, what I can do is I can compute the maximum of this function, and that still should be less than this function. So I might as well take that value and say that's my next point. That's essentially what your maximization is doing. Okay, so in the expectation maximization case, you start with the current case, then at that current case, you are computing like a lower bound function. That function is guaranteed to be below this function. Since it's guaranteed to be below this function, if I find the maximum of this function, which is easy to do, because this is corresponding to complete data, that maximum will still be below this function. And furthermore, that number is good, that point has to be above this point, because this is a lower bound, and here it is actually the same. So you go there, and then you keep doing this, and then if you go do this, basically you will reach the local maximum. That's what EM is doing. Okay, so it's not magic, it just basically finds a local maximum of a complicated likelihood function. Until now you have seen likelihood functions. When you have complete data and Bayes networks with CPTs, the likelihood functions will be unimodal. There will be a single maximum. And just, and then basically there would also be the cases where just simple taking the derivatives and doing gradient descent will work. Here, gradient ascent or gradient descent. In this case, we are trying to go for maximum, so you do gradient ascent. And it turns out that EM is a specialized form of gradient ascent algorithm that works well. So many things sort of all wrapped up in this simple idea, essentially. If you see it this way, it looks like, oh, it's just some other idea of hill climbing, who cares? But actually, it has many, many interesting applications, because the way you're doing this allows you to use unlabeled data, incomplete data, to improve the effectiveness of learning. Yes?
Yes, so what I was wondering is that the simplified function, which is the lower bound function, how can we say that the maximum point of the simplified function will correspond to a local maximum?
No, it doesn't. It corresponds to this point.
Okay.
So then I will reconstruct another maximum here, another point here. Which way it have a maximum, it might come there. So it's all this is doing is it's doing big steps on the function. Normally you would have done the steps using just the gradient. Now you are doing these steps using this reasonably complicated idea where you are first constructing another function which is a lower bound function, which happens to be equal to this function here. And this function happens to be easy to maximize. And because it's a lower bound function, its maximum value will be above this guy and will still be below that function. So then I take that x value and take that function's value there. Okay? And then keep doing this. That's the expectation maximization. So we'll stop here. Next class we'll talk about a couple more easy learning algorithms, Bayesian trees and neural networks.